All right. Seen at this point. There's a lot of cool stuff we'll get to talk about. So it's gonna be fun to go. Better remind me because I was forgetting. This one's good. And I have to draw a picture for it, so it's very relevant for physics. What did 0 say to 8? Nice belt. It's good. Yeah. Anyway, yeah. I was like, again, my wife spent a long time looking for these jokes. It's a clever one, but it doesn't make sense unless you draw it. So, anywho. Last class we did momentum. Had a great time. Did a bunch of problems. It's just add up all the MVs in the beginning and equals all the MVs at the end. We did a bunch of things on it. We saw this gross boulder one, and I said, don't worry about the math. But do remember that in elastic collisions, energy is conserved, momentum is conserved. Hopefully you've been seeing that in your lab, though the numbers might not work out super well, but whatever. So it's a very, momentum, in my opinion, very straightforward. MV plus MV equals all the MVs. Good stuff. All right. Center mass. So we're going to do a few questions to kind of help us get acclimated to what the purpose of it is. And then we'll do the thing. And then I will literally solve both equations in the problem set with you, because there's really only a few permutations of center mass problems. They're all kind of the same thing. Anywho, if I had the following triangular shaped roof with a uniform density, approximately where would you place a vertical beam to support it? I think I clicked the right class. Did it send to you all? Great. I always worry that I have the other class open. Yeah, so do you place it here on point A all the way on the left? Do you place it point B a little bit to the right of that? Point C, which is dead in the middle, or point D way off to the right? There's only one right answer. Talk to the people.
Any object I could press down.
All right, we'll go like 10 more seconds. Give it a guess if you don't know. All right, in 5, 4, 3, 2, 1. I am very happy to hear people chatting in the room. It's so boring when it's quiet. Anyway, so we're getting to center mass. Where's this? Where are you going to put a vertical beam? You all balance stuff in your life, hopefully, probably. We're going to the center mass is like where the center of the mass is. It sounds stupid, but like on this end it gets thicker. On this end, it gets thinner, so the center of mass is going to end up being about here, because if you like took all this mass, it's about equal to like all this mass, and the center of it's in the center. So, great, you put a pillar there, it balances, very nice. If you put a pillar here, there's too much on the left, it's going to tilt and fall, not a good spot. So, how do we do? Yeah, look, it's pretty good. The whole point of this is to show you all that you have experienced this. If you didn't get the right answer, that's all right. So what I want to convey to you all is center mass. And there's a fun little thing you can kind of do. Again, center mass, you basically can take all the mass and like squish it to that dot, and you can work with the object as if it was just that single dot. So this problem and this problem are the same two. Well, if you imagine that this had like all the mass of this big thing, they're the same thing. We're going to squish things to the single dot. And so a couple examples as well. You can do this for yourself. You have to lean against, if you put yourself against a wall, your feet up against the wall, if you slightly lean forward, you will fall over. Like, even if it's just a really tiny amount. So I have moved myself just a little bit forward, and this time I will fall. Try it for yourself. Even if you took yourself just a tiny bit forward, you will fall. Why? Because when you lean, okay, so let's draw you standing. There you are. Wow, all your goodness. If you roughly had to say where your center of mass is, where would you guess? If you took your body and you squished it to a single spot, where would that be? Yeah, so somewhere like in the middle, right? Like somewhere near your belly button kind of ish area. Great, right there. That's about the center of your mass. If you lean forward, what did you do to your center of mass? Which way did it move? It's going to move a little bit forwards. Now, something that trips people up, the center of mass doesn't have to be on the object. The center of mass does not actually have to be on the object. There's a really easy example of this to prove this to you. If you had a hula hoop, where's the center of mass of a hula hoop? If you imagined all that mass, where's the center of it? It's in the middle of the hula hoop. There's nothing there. Sounds kind of weird, but center of mass doesn't actually have to be on an object. A boomerang's another example. We'll talk about things like that. But why does that matter here? If we pretend like all your mass is here, is there anything under your mass to support it? No, that's why you fall. If your center of mass isn't above your feet, you will fall. That's a guarantee. Unless your feet are hooked onto something. And so you all do this all the time without realizing it. The reason I had to put my back up against the wall, you all do this yourself, put your back up against the wall, is because when you lean forward, you stick your butt out. You don't even realize you're doing it, but you're doing it. And by sticking your butt backwards, the top of your body goes forward, your butt goes backwards, they cancel each other out. So you don't even realize it. That's why you put your back against the wall so you can't stick your butt backwards. But yeah, this is going to look awful, but this is really what you do. And your center of mass is still above your feet and you don't fall. If you get really extreme, you will also know how not to fall. You'll stick your leg backwards. So the more extreme thing, if you want to really lean forward, your butt can't stick out and your leg will naturally kind of come up and you balance. It's nothing crazy. What are you doing? You're just making the center of mass above your feet. So that's one reason why center of mass is super, super useful. You got to put a support below it if you want to not fall. The Michael Jackson leans, the classic that people think about. If you all have seen the video, I forget, is it Billie Jean? Which one is it? Smooth Criminal. So Smooth Criminal, yeah. If y'all watch the music video for that, he does this lean where he leans forward and it looks weird. People are whoa, how's he doing that? He's cheating. His feet are hooked on something on the ground so he can pull up on his feet so he doesn't fall. It's impossible for anyone to do that without hooking yourself to the floor kind of thing. So that's why when people say that, whoa, how do you do that? By cheating. He's not defying physics. He's just hiding some of the physics. So, great. Center mass, that's one reason it's useful. The other reason, and I'm actually going to drag this video, it's a little weird that I'm going to play a YouTube video because I'm streaming my class. Things rotate about their center of mass, which is kind of cool. We've been doing a lot of physics problems in this class with all sorts of objects, and you didn't care what the object was. We've done throwing a basketball, we've done cars, we've done, I don't know if I've really given you, balls, random objects. You never cared what the shape of the object was because it turns out if you take that object and you compress it to a single dot, that's what you've been working with. You didn't care about it. We will care about the shape when we start talking about rotating things, but this YouTube video I think is really interesting to show center mass. So what they do here, and I do it in front of you all, but I don't have the proper equipment. So they're going to throw some objects that are crazy shape, tennis racket, things like that. And look at it looks crazy. Man, what a complex path. That thing's spinning and it looks all sorts of wonky. And you're man, if I had to predict its motion, that seems really complicated. They're spinning a disc that's kind of off center. But what's cool is now what they're going to do is they mark where the center of mass is. So they find the center of mass, they put a little highlighted thing. They then have a black light, so that's still the same object, but you only can see the center of mass. And now when they toss it, it looks normal. because it's basically the path that object takes. It's maybe a little subtle. See, the center of mass does exactly what you all have been predicted, that parabolic kind of path. So, yeah, it's DC, and then they do, I think, the hoop at some point. So this is that one that's not really balanced, so it's going to look all crazy because they didn't put it at the center of mass. So they just put it at the center of the object, and it does like a really wonky kind of path. But then when they do the exact same object with the center of mass, it's nice and smooth. Again, all of this is just to say why center of mass is useful. You don't care about the craziness of the object. You just kind of squish everything into it. In every problem you've been doing up to this point, you didn't care what the object looked like. You actually were tracking its center of mass in every single problem. When you're finding its position later on, where you're finding the front of the object, you're finding the position of the center of mass of that object. It was secretly happening in the background. Didn't even matter whether you realized it after the fact. If you didn't realize it, still doesn't matter. But it's just a fun fact. Okay. Again, there's so much with center mass. I'll keep mentioning things as time goes on. But to get us prepared for calculating it, we're going to do a calculation that you may or may not have done in the past. I have no idea. We're going to learn how to calculate your GPA. So your school, your UCF, whatever, you have a GPA across, like a set GPA. This is your GPA, all your classes together. We're going to learn how it's calculated. It's the same calculation for center of mass. So we have 3 classes here. Physics, history, and underwater basket weaving. And you earn different GPAs in these. Physics, you got a 4.0. History, you got 3.0. Underwater basket weaving, you got 2.0. And each of these are worth a different number of credit hours. Physics is 4 credit hours. History is 3. Underwater basket weaving is 5. So these GPAs are going to carry different weights. They're going to carry different weights. Like the one for basket weaving is going to affect your GPA a lot because it's a lot of credit hours. Your GPA is calculated on a per credit hour basis. The one for history is going to matter the least, and physics is going to be in between. So this is what are we going to do first? We're going to weight each of these credits by GPA. So we're going to take the credit for a class, how many credit hours, the number of credit hours, and we're going to multiply it by the GPA, and we're going to add all those together. We're going to add each contribution. So, for example, physics was 4 credits, and we're going to multiply it by 4 GPA. And that's going to give us like some number. Then we're going to do the same thing for history. Then we're going to do the same thing we're going to add them all up. So we're going to multiply the number of credits for underwater basket weaving, weighted by the GPA, and then we're going to multiply the number of credits for underwater basket weaving and multiply it by GPA. Adding the contributions of all the classes together, the higher your GPA, the higher GPA and the more the credits, the bigger the kind of weight kind of thing. So we're weighting each credit by the GPA. Higher the GPA, the more that credit's kind of worth as far as your overall GPA. Or I should maybe rephrase that. We're weighting, yeah, that's fine. This is fine. All right. So add all those numbers up, and that's going to equal a big number. If you add up the contributions of each one, credits times GPA, plus credits times GPA, plus credits times GPA. Fun fact, this is not your GPA at the end. Like 4 times 4 plus 3 times 3 plus 5 times 2. That is not your final GPA. Hopefully obvious. 35 is not your GPA. Hopefully that's obvious. That's your GPA for all your credits together. Now we need to kind of average that on a per credit. So like what's your GPA like for like 1 credit kind of thing? How are we going to do that? We're going to divide the more credits you have, the bigger this number. We're going to divide this by how many credits how many credit hours you had. This number. So this is called a weighted average is what we're doing here. We're weighting each of these credit hours by the GPA. Then we're dividing by all the credits. And at the end of the day, it's going to spit out your GPA. Classes with more credits have a bigger effect on your GPA. Classes with less credits have less of effect. The higher the GPA, the better. All of it's factored in. So 4 plus 3 plus 5. Great. Go ahead and do that. I'll just go ahead and ship the question to y'all. I'll leave the last part actually to you. Again, there's only one right answer. Talk to the people around you after you get some answer. You know, like 10, 15 more seconds if you haven't gotten an answer yet. All right, in 5, 4, 3, 2, 1. Okay. So, all we had to do is divide this by 12, and you get the answer of 2.92. Great. So, what I want to point out here is what you wouldn't do. You wouldn't just add 4 plus 3 plus 2. You wouldn't just add all the GPAs and then divide by 3. If you're doing that, you're neglecting that they're different credit hours. And that's going to weight things. That's why this is called a weighted average. You're not just averaging the GPAs. You're weighting them based on how many credits, and then you divide by all the credits to kind of cancel out that sum, normalize it back down is what normalizing it, and there you go. This is how you do center mass. It's the exact same calculation as this. The only thing that changes are the variables. So if you all were cool with what we just did here, center mass is the same. If you weren't, hopefully as we do more of these, it'll feel more comfortable. But yeah, that's all a weighted average is. If you all see this, we have to do it in X and Y. So we have to do it in the X direction and the Y direction. But it's literally just take the X position of an object times its mass plus the next X position times its mass plus the next X position times its mass. And then divide by all the mass. And then do the same thing in the Y. So instead of GPAs and credits, we have where you're located in the mass of each object. So you'll have several objects. So let me maybe do an easier example. If you had two objects, object 1 and object 2, and maybe we said the origin was here, you have to decide where you're measuring. Remember one of the first questions I asked you on this class is where is demo duck located? And the immediate question was from where? If I said it's 3 meters away, from what? You have to choose an origin. So, for example, if I want the center mass of this object, I'll make an origin. That's my x, y, whatever. This distance is going to be x2. This distance is going to be x1. Now, do note that x1 will be negative. Left and right matter, because otherwise the math won't work out. It matters whether you're to the left or something to the right. So if this is a problem and this is mass 1 and this is mass 2, if I wanted to get the center mass, I would do mass 1 times x1. Maybe I wouldn't. Nothing's writing. Times mass 1 times the other thing. Did my pen die? If so, I'm going to have to finger paint, and that's going to be awful. All right. Mass 1 whatever. Mass 1 times x1 plus mass 2 times x2. I don't know why it's decided to be weird. And you go from there. Put you there. Mass. It just doesn't like the corner. I have decided. All right, well, the next problem is going to be that, and fingers crossed my pen will work then. Otherwise, life is going to be hard for us. Whatever. I'm going to write on the board, and then I'll mass 1 times x1 plus mass 2 times x2 all over mass 1 plus mass 2. Like, that's the idea. That's what I'm hoping to write on the whiteboard, but I'm struggling to do so. So, that's the first problem we're going to do. Yay, mass 1 x1 plus mass 2 x2 all over mass 1 plus mass 2. And you do have to be careful. There's positives and there's negatives. Position is a vector here. So this is a little vector. This is a little vector. Anytime we said where something is located, if you're to the left of the object, it's negative. If you're to the right of the object, it's positive. Up, positive, down, negative. And yeah, best way to kind of see this is we're going to do two different problems. One's going to be in one dimension. One's going to be in two dimensions. And that'll cover the gambit. So, find the center of the mass of the Earth-Moon system using Earth's center as the origin. Oh, I didn't tell you the origin. I didn't realize that was in the problem. The mass of the Earth is 5.97 times 10 to the 24 kilograms. Mass of the Moon is 7.36 times 10 to the 22 kilograms. Distance from the Earth to the Moon is 3.85 times 10 to the 8 meters. If the radius of the Earth is 6.37 times 10 to the 6 meters, how far away is the center of mass from Earth's surface? That's a lot of numbers and words. Draw a picture. Always draw a picture. So you have the Earth, you have the Moon. We could put some things. This distance here is from the center of the Earth to the center of the Moon. That's important. Probably hadn't even thought about that, but it is actually a really, really important thing here. So this is 6.7 times, This is 3.85 times 10 to the 8. I'm going to use that E8 notation. So we're working with really big numbers here. When you all get to Physics 2, you're going to be working with a lot of small numbers. I highly, highly recommend when you all do this stuff to use the E notation because it makes your it results in less errors in your calculator. It's often how you're going to plug it into your calculator. Do whatever you're comfortable with, though. If you prefer the times 10 to the whatever, go for it. All right, and we got the mass of the Earth is 5.97 times 10 to the 24 kilograms. Sadly, we weren't able to do universal gravity. I didn't find a good home for it this semester. So we didn't get to work with these big numbers. But this is a complete aside, but I think it's really important. You're just going to look at this and say, that's a number. I'm going to go ahead and write out this number, not in scientific notation, because sometimes we see numbers and we don't actually think about what they mean. The mass of the Earth is 5, and then I need to hop the decimal place 24 times to actually write out this number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. The mass of the Earth is such a giant number that there is no way your brain can get around. Like, 1 billion, trillion, quadrillion, quintillion, then sept, like I don't even know what those are called. And then here's your mass, roughly 70 kilograms. The Earth and the universe is so much bigger than you can actually conceive. Something you all may not, the Earth has the crust and the mantle. we haven't even gotten close to like digging through the crust of the Earth. And you look at a picture, the crust is like the tiny little skin on it. The Earth is so massive that you can't like imagine how big it is. And there's some benefit of that to realize, oh, the world's so much bigger than you realize. Sometimes things can feel a lot smaller or bigger or whatever. But it's sometimes good to just kind of be like, you can go two ways with this. I'm going to give you the positive way. Your problems in your life matter. They are significant, 100%. But sometimes when you take a step back and kind of look at the whole, like, wow, it's a big stuff out there. Within context, it can sometimes make things feel a little smaller, which can sometimes take stress off of things. What I don't want you to do is go to the far extreme and say everything's so big, nothing I do matters. Life is meaningless. But whatever, that's my complete side tangent thing. But it's fun to mention, there's a lot of like, world's big, universe is big. It's just a fun little aside. Whatever. There's the mass of the Earth. Then we got the mass of the moon. Mass of moon, mm. Not near, it's still really, like, it's only times 10 to the 22. It's still absolutely massive. It's stupid big. Okay, something that's kind of helpful here. So in general, you remember, you always need to decide where 0 is. Now, I say you need to. In this problem, I tell you where 0 is. So I want you all, this is a good practice. On your picture, draw where 0, 0 is. Where x equals 0 and y equals 0. It's given in the problem. In the problem, it says Earth's center is the origin. How is that useful? That means that basically our coordinate axis is like this. The Earth's center is my origin. That is 0, 0. Every distance is measured from there. That's really, really important when you're doing center mass. If you don't know where you're measuring with respect to, you can't get a number. Or at least not a consistent number. So, this is all going to come into play. But yeah, when you're doing these, if you want, you can make a little like coordinate system there, if that helps. Okay. Great, we got a picture, awesome. Remember, we're actually going to kind of skip step 1. I want to train you all to actually start moving to the next. What are we solving for is actually one of the first things you want to actually think about. I know we jumped to the picture, but picture / what are we solving for are kind of the things you want to start a problem with. So what am I solving for? In part A. Yeah, find the center of mass. Now this is a one-dimensional problem. Even though these objects have like x and y, the y's are all going to like smush down to the middle. So we're not going to worry about y. We're going to do just the x center of mass. The y center of mass is going to be 0. It's going to be on that line. So I'll show you a problem after this where that's not going to be the case. So yeah, we're going to add up the position of each object times the mass of each object. And then we're going to divide that by all the mass. That's what we're solving for. And I probably should have put that in step 3 instead. This is, yeah, if you're doing center mass, this is what you're going to do. It's just whether or not you need to do it in 2 dimensions or not. Okay. How many objects are there? 2. So I need to add up 2 things. Both of these sums should have 2 terms in it. If you have 5 objects, you should have 5 terms. 10 objects, 10 terms. 100 objects, 100 terms. If we had an infinite number of objects, you would do an integral. You don't need to do that because that's calculus. So here's how we're going to do this. Technically, there's little indices here. Xi, mi. This I is just the indice. Object 2, be consistent. Let's just call the Earth 1 and this one 2. What is the x position of my Earth times its mass? Yeah, that one's going to be nice and easy. The x position of the Earth is going to be 0. Why? It's at the origin. What's the x position of object 2, the moon? See if you can figure that out. Then we're just going to chuck the numbers in there. So this is how you do center, and then you divide by the total mass. And that's it. That's how you do center mass. So yeah, x center mass is going to be, what's the x position of the Earth? 0. What's the mass of the Earth? Sure, we'll put it here just for continuity's sake. 5.97 times 10 to the 24 plus what's the x position of the moon? How far away is the moon from the origin? Oh, look, we have that value. 3.85 times 10 to the 8 times the mass of the moon, which is going to be that 7.36 times 10 to the 22. And you divide all of that by the total mass of the system. So the two objects together. If you had 5 objects, you'd add all 5 objects up. If you have 2 objects, you add those 2 objects up. And this tells you the center mass of the Earth and the Moon. You plug all that in, you're going to get roughly here. Just for the sake of giving you as much time, I'll go through the motions in my calculator. 0. Oh, and I recommend plug this whole big blob. If you want, you can do the top and then divide the bottom. I've mentioned this to a few students now. Once you have an equation, my recommendation is plug that entire equation in one go in your calculator. It makes it much easier to check your work. Because then I just look at what I typed and I look at what's written and I can just do a one-to-one check. Whereas if you break this, if you did the first part here and then the second part, if you do it in a bunch of steps, it's really hard to check your calculator for that. That's my experience. So, anyway, the first term is 0. I'm not going to plug that in my calculator. 3.85 E8 times 7.36 E22 divided by, you got to be careful on the bottom, put the parentheses. I wrote them down for a reason, so that I didn't forget to put parentheses. Plus 7.36 E22, and you plug that in your calculator and you hit enter, and you get the center of mass is about 4.67, or 4.69, I think is what I get. And you look at this, say, why does that say 4.64? I think I used a slightly different number. Maybe I used the mass of the Earth was 5.92 or something. 972. Whatever. Double check my numbers. Yep, looks good. All right. Great. Next thing I want you all to do is I want you to put a dot on your picture where that actually is. It's good practice. You just found center mass. Where does that actually correspond on your picture? Put some dot there. All right, so the key to this is it tells you the radius of the Earth, and this is what's going to help us answer the next problem. The radius of the Earth, the entire radius, is 6.37 E6 meters. That's the radius of the Earth. It's a big number. It's 6 million meters. Doesn't compare to the kilogram, but it's still a really big number. 4.69 times 10 to the 6, they have the same times 10 to the 6. So one of the ways you can do, so that basically kind of cancels out, and that means we're about 2/3 of the way. 4.69 is about 2/3 of 6.37, because they have the same order of magnitude. This one's 4,700,000. This one's 6,300,000. 4 million is about 2/3 of 6 million. So you're about 2/3 away from the center on here. So that's the center of mass. Why does that matter? Well, that's what the problem's asking for. Great. Conceptually, what's kind of interesting about this is where the Earth and the Moon orbit about. The Moon doesn't orbit the center of the Earth. The Earth doesn't orbit the center. The Earth and the Moon actually orbit a shared point, which is the center of mass. Every time you have objects out there, if you have multiple objects, they orbit the center of mass of all those objects. So a really extreme example of this would be if you had 2 stars. You had a star and then you had a slightly smaller star. They're going to actually orbit some spot in between the two, not dead center. What's that spot? It's the center of mass. Another interesting application of center of mass. So yeah, the Earth actually orbits a spot that's shifted from the center of the Earth, which is really weird sounding, and it's kind of hard for me to visualize that for you. But it spins about, so the Earth here kind of spins around this green dot kind of thing, which is funky to visualize, but it's a thing. All right, the other reason we did this mathematically is part B says how far away is the center of mass from Earth's surface. If you know the radius and then you know how far away you are, what you're solving for in part B is this little distance right here. So part B, how far away am I? You're going to take the radius of the Earth and you're going to subtract. If I have this big number here, we're going to take this, 6.37E6. We're going to subtract where we're located, and that's going to give me how far. If you're not sure why, it comes from the picture. You all have this big purple arrow right here. So you all know how big this big purple arrow is. You all know how big this is. The distance from the surface is what's left over. I'll do it on another slide. It's just it's a little logic thing. It's not physics per se. So, well, I'm going to keep that because I don't want to rewrite that. I'll draw it nicer on the next picture to make sense of it a bit more. The next problem says, how far away is it from the center of the Earth? Here's my Earth. I'm going to make it really exaggerated. Here's my radius. So that's my 6.37E6. This is where a picture comes in handy. Here's my center. That distance is 4.69 E6. What am I solving for? I'm solving for what's left over. That tiny little bit there. So you can see it visually. If I subtract them, I get that distance. So if that was tricky, but that's a good logic one for y'all to figure out. It's a logic test. Can you figure it out from your picture? You're going to encounter stuff like this in physics 2 and all that. Given two distances, can you find another distance? Given two angles, can you find another one? So it's 1.68 e to 6 meters. Yeah.
If you were to ask a question like that, how would you phrase it?
How far away is the center of mass from the closest point on Earth's surface? Yeah, is how I'd phrase that. Because technically you could argue I could use this distance to Earth's surface or this distance. So I'd say to the closest point. Yeah, and I'm going to straight up tell you, I probably wouldn't do one like that. But it's a good little logic test. Can you do that? Now, if you notice, I actually put the answer as negative because I am negative 1.68 meters from the surface, or another way of writing this, in this case, I am to the left of the surface. Just reminding you all, lefts and rights matter. I'm not to the right of the surface, I'm to the left of it. If I instead said it was positive, then I'm saying I'm out here, which is not true. So, tiny little thing. Great, center mass. We'll do one more and then we'll call it good on center mass. The next one's just going to be two dimensions. All right, 3-point masses are placed in a triangle. So you got 3 dots. You got one on the bottom left, that's 100 grams. One on the bottom right, that's 150 grams. One at the top, that's 75 grams. Find the center of mass of the system using the location of the 150-gram object as the origin. I will always tell you what the origin is, otherwise there's an infinite number of correct answers. I need to know where you're measuring from and to. So draw this picture, then we're going to draw the origin on there. That's where everything's going to be measured with respect to. And then what I also want you all to do is I want you to give me the x and y coordinates of all 3 objects. We're going to need that. To find center mass, you need to know the x and y location of every object. So draw your little coordinate system. Write the x and y coordinate of all 3 objects. And if you're in the lab this coming week is center of mass. Yay. So all I've drawn here is I drew where the origin is. I told you I'll use the 150 gram as the origin. That's where you draw your XY axis. And then I put little parentheses next to each one because XY coordinates. That's how they're like traditionally written. Parentheses, X comma Y. Now these from centimeters to meters. And when we do this, I'm also going to convert grams to kilograms. Technically, you don't have to. However, if you don't know why you don't have to, rule of thumb, just convert. It's always good to convert. Anytime you see centimeters, it's always good to convert it to meters. Anytime you see grams, it's always good to convert to kilograms, unless you know why you don't need to convert it. And I'll talk to you all about why. Center of mass is one of the few cases where you don't actually have to do unit conversions, but you still have to be careful. So I'm just going to do unit conversions because that's safer. It's always safer just to convert your units. So, anywho, which one is going to be which? We're going to make the 100 gram one object 1, this one the 150 gram object 2, and the 75 gram object 3. Just makes it easier to keep track of what's what. So the 100 gram one, and this is where you might have made a mistake. Its x coordinate is negative 0.04. Again, I'm converting to meters. If you put it as positive, then you're saying it's to the right of the origin. It's not. You got to be careful. These are vectors. You got to be careful with location. Position is what we're using here. Position is a vector. Where you're located is a vector. If I say I am negative, my x coordinate is negative 4 meters, that means I'm to the left of the origin 4. If I say it's positive 4, that means I'm to the right of the origin 4. If you don't put positive and negative, I have no idea which direction to go, left or right. And that makes a big difference. The y coordinate is here is 0 because it's not above or below it. Object 2, it's located at the origin, so that's nice and easy, 0, 0. Object 3 is located at x equals 0, and its y coordinate is positive 0.03 because it's above that. And again, I'm using meters here. I converted it all just to stay on train with that. So great, we got our picture. What are we even solving for? The reason I know I needed coordinates, I'm solving for center of mass. Center of mass, already mentioned this is vectors. Everything here is vectors. Location or position. Center of mass is a position. It has an x and a y component. You've got to do them separate. You cannot do this all in one go. You have to do this separately. You have to find the x center of mass, and then you have to find the y center of mass. And then if you want to know its total distance from the thing, great, you can do things there. So how do we do that? It's just doing the same thing twice. Take the x position of each object and multiply by its mass and add them all up. Then divide by all the mass. Take the y position for each object and divide by the total mass. I had the exact same problem in my last class of space. And divide by all the mass. Now what's very important here, and what I saw a lot of people not do, is a lot of people, like in my studio class this morning, a lot of people were like, oh, object 3 isn't on the x-axis, so when I do x center of mass, I don't include it. That's wrong. Anytime you're doing center of mass, how many objects are here? 3. I should be adding up 3 objects every single time. I don't care where they're located. You better add up 3 things if there's 3 objects. If there's 5 objects, add up 5 objects. If there's 7 objects, add up 7 objects for x and for y. You need to include every object in this calculation, regardless of where it's located. Now, we will see that we'll see it when we see it. So, yeah, so for x center of mass, and I'm going to go ahead and take this, and I'll make it blue. So x center of mass is going to be, just to write this out in variables, the position of object 1 times the mass of object 1 plus the x position of object 2 times the mass of object 2 plus the x position of object 3 times the mass of object 3. Three things. Divide the mass of object 1 plus the mass of object 2 plus the mass of object 3. 3 objects, you add them all up. Yes, some of their x coordinates are 0, but what people did got in the bad habit, or like what I saw was a mistake then, is they then didn't add their mass in the bottom. Just because their x coordinate is 0 doesn't make their mass disappear. So that's the key to center of mass. Every object needs to be represented. Yeah, sure, if the x position is 0, that term will go away, but don't make that decision beforehand. Like, make sure you're including everything. Otherwise, you might forget to put the mass in the bottom. And then at this point, yeah, it's just plug-in stuff. And so then we just put the x position of object 1. That's negative 0.04, and we're going to multiply that. There's no way I have enough room here. I'm going to take all of this. I'm going to take all of everything. And put it over here. And so even if the math, I don't know, I wouldn't say this is bad. I feel like this is a pretty straightforward process. It's my hope, at least. So yeah, the x position of object 1 is negative 0.04 times the mass of object 1. I'm going to convert that to kilograms just to keep with good practices. X position of object 2 is 0. Mass of object 2 is 0.15 kilograms plus x position of object 3 is 0 times 0.075 kilograms. So yeah, the second two terms are just 0 and disappear. Great. But I still have to put their masses here at the bottom. 0.1 plus 0.15 plus 0.075. Just because their x position is 0 doesn't mean you ignore them on the bottom. And you just plug that in. So yeah, this term goes away, this term goes away. It's a nice simple thing. So negative 0.04 times 0.1 divided by the total mass. 0.1 plus 0.15 plus 0.075. And we get our x coordinate is negative 0.0123 meters. I worked in meters, so it spit out meters. The reason why you could have actually left everything in grams is because all your mass is up here. If those are all grams and your bottom's all grams, grams divided by grams disappears. And then you're left over with whatever your distance was. So if you did it all in centimeters, it will spit out centimeters. No, whatever. Try it for yourself. Have fun. If you want to do the y coordinates, it's the exact same process. Just replace things with y. So there's this one. So if you want to do y center of mass, it's y1 times mass 1 plus y2 times mass 2 plus y3 times mass 3 divided by mass 1 plus mass 2 plus mass 3. It's the exact same equation as the other one, just with y's instead of x's. This one I'm going to let you all do on your own. You can try this one out in your own time. You have them all here in the picture. Chuck them in, see if you can figure it out. But for the sake of time, I'll kind of jump forward. We'll do a couple more questions, and then I'll do a very quick intro to fluids. But yeah, this is like the worst case scenario that I could give you all. Find the center of mass of objects that have x and y positions. I will have at least one, maybe two questions on center of mass. So yes, it's something you need to be able to do. Your lab this coming week, you're going to do center of mass. That's extra practice if you're in the labs. And yeah, that's it. So it's good stuff. All right, great. We already talked about this. All right, so this is kind of interesting. When it comes to center of mass, the last application I'll mention to you all is things, and we actually kind of already slightly mentioned this. Things will spin. If you spin an object, it's going to spin around its center of mass. That's what it's going to spin around. So if y'all take a tennis racket and you throw it in the air, it's going to spin around its center of mass. There's reasons related to torque and things like that. So there's two examples here. One is your tire. If you all have ever gotten your tires to get balanced, whenever you buy a tire, they have to balance your tire. What does this mean? Your tire is connected to an axle, which is connected at the center of your tire. It is not a guarantee that the center of mass of your tire is at the center. You may be like, well, of course, your tire is complex. There's rubber, there's wire in it. It's not perfectly balanced. The center of mass could actually be over here, and that's bad. If you all don't have if your tires aren't balanced, they get really rumbly. They want to rotate around that red dot when your axle's connected to that blue dot, and that puts strain on your axle, and it's really bad. So if you all look inside your tire, what you will actually find is there's lead weights that have been like glued / stuck to the inside of your tire at various points. Why are those there? They shift the center of mass back to the center. It needs to be as close to perfect as possible, because if it's slightly off, it does damage to your axles. Another example of this that's maybe one that's easier to experience, if you've done laundry, you cared about center of mass. You're like, what is he talking about? Your laundry machine spins. If you have like one of those top-down laundry machines, if it's sideways, it's not as big of a deal. If you all have ever done a laundry machine where like you put your clothes in the top of it and it spins like this, if you ever put a bunch of sheets in there and they end up all on one side, it makes an awful, like awful noise. That's because when all your sheets, so it's spinning around the center, if all your sheets are on this side and they get filled with water, so it's a lot of mass, it shifts your center mass over here and it tries to rotate about that and it clangs a bunch. And how do you fix it when your laundry machine's clanging? You redistribute the sheets around the outside to shift the center mass back to the center. Didn't realize you were doing it, but yeah. If your laundry machine starts clanging about, and mine does it all the time, especially when you do bedding and things like that, they all tend to clump up on one side. The solution is to separate them, spread them around, so that the center of mass is in the middle. Another example that's kind of cool. Otherwise, it's awful and you will break your laundry machine. You want everything to be nice and uniformly distributed. This is really bad. It will clang up a storm, whatever. So, okay, last question, and then we'll do a very quick kind of overview of fluids. If a 70-gram mass was instead 6 centimeters above the 150-gram mass, what would happen to the X component of the center mass? So I just took the triangle and I stretched it upwards. So instead of it being, instead of the 70-gram mass being 3 centimeters above it, now it's 6 centimeters. Does my X center of mass, the X component, shift to the right, shift to the left, or stay the same? Give you like 15 more seconds. All right, in 5, 4, 3, 2, 1. All right. If you shift an object upwards, did I move it left or right at all? No. So what happens to the X center mass? Absolutely nothing. X and Y are independent of each other. X and Y are independent of each other. If you don't change anything in the X, why should anything change in the X? So, yeah. If you all remember the equation for the X center mass, it was X1, mass 1, plus X2, mass 2, plus X3, mass 3, all over the total mass. If I don't change any of those numbers, then nothing should change. Moving it upwards, I didn't change the x-coordinate of any object. So, yeah, this is just a question that kind of shows you x, y independence, and it's kind of a reminder of x and y independence. They don't affect each other. So, anyway, great. That's center mass. And that's momentum. And so now we just have our last week of fluids. And then that'll be everything on the exam. So I'm going to warn, so fluids is going to have a lot of equations. But the nice thing is, so ironically, when you have more equations, you might think, oh no, that's terrible. More equations, in my opinion, makes problems more straightforward. Because like with energy and momentum, you have to build the equation. In this one, you just write down your givens, you write down what you're solving for, you find the equation that has those things, chuck it in there and solve. Kinematics is that way. So I put up in the formula sheet, this entire row is fluids. And then after that, we'll get to rotation stuff, but that's after the test. So the good news is, some of this should hopefully look familiar. Rho equals m over v. Hopefully you've seen that before. If not, don't worry. It's going to show up in the next slideshow. It's density. Density is mass over volume. This is pressure. That's really, really important. And then these couple other ones are going to be funky, but we'll talk about those. Those are going to be new probably to you. This last one is called Bernoulli's equation. And it's like, oh my gosh, look at that crazy equation. But I really hope that you all look at this and say, parts of that look familiar. I have a 1/2 times a number times velocity squared. I have a number times gy. My hope is when you look at this, that you're like, wow, that looks like energy. Because Bernoulli's equation is just conservation of energy for fluids. This term right here, 1/2 rho v squared, is basically the kinetic, like, it's not quite energy, but it's basically the same idea. Energy of a moving fluid. What's this one? It's kind of like the gravitational potential of a fluid. mg, just replace m with rho, and replace work with pressure. So if you're cool with energy, this last thing is just energy with fluids. Anyway, and there's some, it'll be fun to talk about. So, jumping over fluids. We're probably just going to talk about density today, so I'm going to kind of give you all a quick overview of what we're going to talk about, and then talk about density a little bit, and we'll kind of call it good there. So, fluids. All right, it's got a lot of learning objectives because there's just a bunch of equations. Each one has its own thing. So, we're going to talk about density, which again is hopefully something you've learned before, but we might do a problem that's like a little more complex than you've seen. Pressure, what it is, and how it relates to area and force. We're going to talk about how pressure varies with the depth in fluids, something you all know. You get deeper in the ocean, pressure goes up. Pascal's principle, Archimedes' principle, velocity and cross-sectional area, and Bernoulli's equation. Lots of names because lots of people contributed. Archimedes, that one's really interesting because that's like BC. Archimedes, he discovered this, I think it was BC. Discover this principle. Like, he didn't even have the math for it. He just, you'll see it when we see it. It's cool. All right. So this is like a classic. Most people have probably seen this question before, but it gets us ready for density. What weighs more, a ton of bricks or a ton of feathers? The word ton here is a measurement. If you want, you could replace this with what weighs more. A ton is 2,000 pounds. In case you didn't know that. What weighs more? 2,000 pounds of bricks or 2,000 pounds of feathers? Chat with people. There's only one right answer. We'll go 10 more seconds. All right, in 5, 4, 3, 2, 1. Boop. So I could have also asked, what has more mass? A ton of bricks or a ton of feathers? The answer is it's the same. It's the same weight. Weight is just mass times gravity. G is the same in both. They have the same mass. The whole purpose here is Sure, ton of feathers is a giant pile, and a ton of bricks is like a tiny little pile. They have the same mass, if I say ton. Why does one take up so much more volume? Because they have different densities and different volumes that you would need to accomplish that. Yeah, so I mean, density, I really hope you all have seen density before. If not, here it is. How tightly packed together the atoms are. It's really, really important when it comes to fluids. It matters because fluids have different densities, but also so do physical objects, and we're going to talk about buoyancy and things like that. The Greek letter is rho, which is it's a P without so it's not a P with a little thing like that. It's a slightly angled P. What's really disappointing is this morning I was like, I wonder what capital rho is. This is going to be really disappointing. It's a capital P. Whatever. So sadly, that's one of those we don't get a separate letter. Whatever. Rho, there it is. It's mass over volume. Now, something that's going to be a reoccurring theme in fluids. It's probably the most annoying thing about fluids, at least in my opinion, as I was going through the content. There's a lot of different units for the same thing. So that's a really common theme in fluids. So for example, density was so this is just a really fun fact. The metric system, someone had to decide it at some point. How was it decided? It was actually based on the density of water. At some point, someone said, I want the density of water to be 1 gram per centimeter cubed, and then grams and centimeters were actually based on that. How they chose how much a kilogram is literally 1,000 centimeter cubed of water. That's how a kilogram is decided. How did they decide how much a centimeter was? They just picked things. So, anywho, 1 gram per centimeter cubed is the density of water. Now, what you don't want to do, 1 gram per centimeter cubed, if I wanted to convert that to kilograms per meter cubed, it's very tempting to just say it's 1. Because you're grams, that's going to get smaller, but centimeters is going to get big. They're going to counteract each other. It doesn't work out that way. This is not true. When you we'll do the conversion. I mean, you can see the answer down here. 1 gram per centimeter cubed is 1,000 kilograms per meter cubed. Just to kind of talk through that, literally what density means, if you just think, so the units mean something. They literally mean if I have a box of water that's 1 centimeter on a side, I'm very pleased with my box. If I have 1 centimeter, a box, 1 centimeter by 1 centimeter by 1 centimeter, it's going to have a mass of 1 gram. That's literally what it means. It says, for every centimeter cubed I have, I get 1 gram. If I have 5 centimeter cubed, 5 grams. 10 centimeter cubed, 10 grams. So let's go to the extreme, and let's make a box that's 1 meter by 1 meter by 1 meter. And I can't quite fit it on here compared to the other one. 1 centimeter is 1/100th of a centimeter, so I can't quite fit it, but just pretend like this is accurate. So this is a box that's 1 meter by 1 meter by 1 meter. So let's go ahead and figure out the mass of that box by doing this unit conversion. So we're actually going to do it correctly. And I'm going to do it the way that I like, that I've seen that you all have kind of learned to do it. So first what we're going to do is we're going to convert grams to to grams to kilogram. So how many grams are there in a kilogram? 1,000. So we're going to do 1 kilogram over 1,000 grams. That way our grams cancels. Yay. Now we need to convert centimeters to meters. How many centimeters are there in a meter? 100. So there's 100 centimeter per 1 meter. We put it on top so it cancels. But here's the problem. Centimeters is cubed. So how many times do I need to do that? I have to do that 3 times. If you all do the math here, if you just plug that in a calculator, you will find that okay, 1 gram per centimeter cubed is not equal to that. But if you do the math, I'm just going to do it just to be safe. 1 divided by 1,000 times 100 cubed. Yeah, okay, well, this is fine. So these are not equivalent. No, sorry, they are equivalent. What am I saying? This is equal to 1,000 kilograms per meter cubed. They're both the density of water. Both these are true. Density of water is 1 gram per centimeter cubed. Density of water is 1,000 kilograms per meter cubed. It's the same number. It's the exact same amount. So what does this mean? It means if you had a box that's 1 meter, and this isn't that big, like 1 meter, it's a meter stick. If you made a box of water that's 1 meter by 1 meter by 1 meter, it weighs 1,000, it has a mass of 1,000 kilograms on Earth. If you're like, that's not that big, that's 2,200 pounds. It's 1 ton. Rough. It's more than a ton. 2,000, 1 meter by 1 meter by 1 meter. If you had 3 of those, it's the massive thing of a Cybertruck. 3 meters cubed of water is the same mass as a Cybertruck, I believe. I think it's like 7,000 pounds. I think. I have to double check that. Water's heavy. Water's really heavy. And that's something most people don't really realize. That's why tsunamis are so crazy. Like when a tsunami, or like when water levels rise, like when the hurricanes hit and water came through Tampa, the amount of weight behind like even a slow moving thing of water, that's why it knocks people over so easy and it's super dangerous and you get carried away because it's a lot of mass. And like we've learned, if you have a lot of mass, you have a lot of momentum, even if you're moving really slow. So just one of those things you want to realize. Okay, so great. That's another unit conversion. Another thing I need to point out to you all is that 1 centimeter cubed is the exact same thing as 1 milliliter. Like, they're the same thing. So the density of water is 1 gram per milliliter. Again, there's so many terms for the same thing. So, density of water is also 1 gram per milliliter. That's true, same thing. Or, and this is kind of annoying, equals 1,000 kilograms per meter cubed. 1 liter is equal to 0.001 meter cubed. So if you want to do that unit conversion, that's also a mess. A meter cubed is not equal to a liter. That's, again, a tempting thing to want to do, but that's really obvious when you think about it, that they're not the same thing. If you go to the grocery store and buy like a liter of milk, you're not buying a meter cubed of milk. So this is just kind of an annoying thing that you all have to keep track of when doing fluids. If you want to convert units and things like that, you just got to be careful. And yeah, in general, I like to work with kilograms per meter cube, but whatever. Okay, so let's practice. I think I already answered. Good. I'm glad I went back to do this. All right, water has a density of 1 gram per centimeter cubed. What is the mass of 230 milliliters of water? Classic question. Some of my answers are in grams, some are in kilograms. There's only one right answer. In general, we do want to keep working with kilograms and meters because they're base units. Like, that's the ideal. So that's why we want to practice this skill. I'll go like 10 more seconds. All right, in 5, 4, 3, 2, 1. All right, so, we got our density, we have our volume, we're solving for mass, density is mass over volume, rearrange that, mass equals density times volume, awesome. So there's a couple ways we can do this. We can get the mass by taking the density, and I'm actually going to put the units in here just so we can see that 230 milliliters is the exact same thing as 230 centimeters cubed. So if you all do this, you can see those cancel. We spit out 0.23 kilograms. They're the same thing. Great. That's one way of doing it. If instead you wanted to work in kilograms, you'd say it's 1,000 kilograms per meter cubed. Then the unpleasant thing is you got to convert milliliters. So 0.23 liters. And then I told you all a liter is 0.001 meters cubed. So then you'd have to multiply that by 0.001 and you get 0.00023. And if you multiply those together, you get this exact same answer. 2 ways a Sunday. Whatever. So, which way is better? Neither. They're just whatever one gets you the right answer. Yeah.
Why is it necessarily kilograms if both kilograms and grams are like both mass? Because I'm just thinking of it like chemistry-wise, because I'm in chemistry.
Mm-hmm.
So.
Yeah. So why do we want kilograms? Like, why do you want to get to kilograms? Or so 1,000 grams is 1 kilogram.
Is that mainly because kilogram is like the widely used like base unit?
The reason, so kilograms is what's going to work in our equations. Yeah, if we're ever in an equation you see mass, our equations are tuned for kilograms, kind of thing. For example, if you wanted to find the weight of this, the force of gravity, you would need to multiply the mass in kilograms times 9.8. If you use the grams and you multiply that by 9.8, you won't get the correct thing. So yeah, it's a great question. Physics is that. All right, so the last thing I'll mention to you all, we're not going to solve this problem because we don't have time, but the problem we're going to solve next class is we're going to find the density of a steel gas can that holds in gas. And the key to this is we're not finding the density of the gas in it. I gave you the density of the gas. You're finding the density of the entire object, the steel and the gas together. Why is this useful? Your body is really complex. If you measure the density of your body, it's not the density of flesh, it's not the density of bone, it's not the density of muscle. It's the density of all of it together. So we're going to learn how to take a bunch of different objects and find the density of them all together. And then by extension, you could do backwards. So, yeah, that's what we'll do next time. Have a great weekend, y'all. Good luck with momentum, energy, practice, all that good stuff.